So the last time we're looking at conditional probability. Let me just remind you where we ended the last time. This is where we ended. We were looking at the green balls and then being drawn. I hope you guys remember this question. The red and green balls. We ended by calculating all of the probabilities.
Yes.
And then we also computed this conditional probability. Look at that, conditional probability. And then I told you to go and look at this one for yourself. Do you remember?
Yes, Doc.
I hope you've done it already.
Yes.
Yes.
So it's good you are always able to do things quickly, because this lecture, every week there's a test and every week there is a homework. So you can imagine there's a test, there's a homework. There's a test, there's a homework every week. So when you do it earlier, you are sorted. All right. So today we want to continue looking at the conditional probability. And I want to start by giving you a contingency table. This is a cross-tabulation table of 100 students cross-classified by their goal. And you learn that. Their goal is that you want the student to achieve some grade. Okay? You also want the student to achieve some popularity, and then also their interest in sport. So some of the students, their goal is that I want to do well in my grade. Some of them, their goal is that I came here to be popular. Others, I came here to engage in sport. So this is a cross-tabulation table. Now, in order for you to use a certain letter to represent things, a student is selected at random, and we are using the letter J to represent that the student girl has been selected. And we are using S to indicate that a student wants to excel at sports. What do you think that B will be representing?
A student boy.
Nothing. That's not. What do you think that B will be representing? Follow the pattern.
Doctor, a boy is selected.
A student boy, not just a boy. A student boy is selected. Okay. What do you think that P is representing?
The student wants to be popular.
I can't hear you, Albert. When you talk, I can't hear the one. I can't hear a lot.
So I was saying that the student wants to be popular.
Okay. A student wants to be popular. Okay. So first thing I want you to do is to find the probability that a student girl is selected. And then find the probability that a student wants to excel in sports. It's very simple. This one you're just picking. Okay, so a student girl wants to be selected will be what? Of course, it has to be relative to the total sample. And what is the total sample here?
151 people.
So the first one will be what? Emily?
Doc, it will be 53 over 100, so 0.53.
And Jerry, the second one, P of S.
P of S is 20 over 100.
All right. So these things are quite carefully executed here. Okay. Now, what is the probability that a girl is selected and she wants to excel at sports? How will you write that? What is the probability that a girl is selected and she wants to excel in sports? What are we looking at? Is P of what?
No, P of G intersection S or S intersection G.
Very good. So I want each one of you to find P of J intersection S. It's fairly simple. The table is there to guide you. It's fairly simple. Anybody? Albert.
It will be 0.7.
Very good.
Over 100.
Excellent. So that will be 7 over 100. Okay. Now, these are the warm-ups. We are going to the real deal. Now, let's go to the next one. What is the probability that a student wants to excel at sports, given that a girl is selected? A student wants to excel at sports, given that a girl is selected. Again, look at it before I show you the table. What is the probability that a girl wants, what is, given, I've been forgetting the question. A student wants to excel at sports, given that a girl is selected. A student wants to excel at sports, given that a girl. What kind of probability is this? How will you write that?
Conditional probability.
Conditional probability of what? Given what?
Of S stroke
G.
G stroke X equals probability
No,
of G
stroke J.
S.
No, it's stroke J.
Yeah, okay. Probability of
Yes.
S stroke G over probability of S.
So it is a probability of S stroke J, which is conditional. So now that it's conditional, that would be equal to what? We've looked at conditional probability multiple times.
Over, is it going to be equals to probability of S intersection G over probability of S?
No.
Doc, it will be probability of S intersection G over P of J.
Exactly.
So it's going to be 7 over 53.
Okay.
Exactly. Okay, it's going to be 7 over 53 because it's going to be the probability of JS. Now, please note that J intersection S is also the same as JS.
Okay.
It's the same as JS. I mean, if you look at the top here, it's 0.7. That's the same 0.7 at the numerator here. All right. Now, let's go on. Let's look at some multiplication rule under conditional probability. We know that this is the formula for conditional probability, that the probability of A given B is the probability of A intersection B relative to the probability of B. We know this, we've seen it 100 million times. Now, if you cross multiply, that means the probability of A intersection B is what?
Probability of B times probability of probability of A given B.
Or it's also the same as what? Because remember that the intersection is irrelevant. Okay? It matches both B. So you are saying that it should be a multiplication of P of probability of A given B multiplied by probability of B. Okay, these two multiplications.
Yes.
Which also means that that same A intersection B will also be what? Because if this multiplication works and the intersection is for both A and B, and A has come first here, giving B, multiplying B, then we can also say that B can come first, giving A, multiplying A.
Yes.
You get
Yes.
it? This one.
Yes.
Albert, are you following?
Yes, Doc.
You have to follow before we do the test. You don't understand arts. Okay. Keep this in mind as we look at the law of total probability. Sometimes it's called total probability theorem. The law of total probability. Now, let's assume that we have I think this one should come. We have AI all the way to AK. So we have, mutually exclusive events from AI, all the way to AK. They are mutually exclusive here means that they can't happen at the same time. And A intersection J is an empty set, or it's 0. And this A intersection J, both the AI to AK are collectively exhaustive, which means that at least one of them can happen. And these are all information you have in the sample space. Okay, so let that be our first thing. If that is the case, we can then say that for any other event B, because we are talking about A, we are talking about A, we are talking about A. For any other event B, we can then say that the probability of that B is going to be the total probability of the conditional probability of B given A multiplied by the probability of A, all the way up to the conditional probability of P of B given A, AK, multiplied by the probability of AK. In other words, the total probability, as long as we are dealing with two events here, okay, the total probability is going to be the sum of this. And this sum of this, check it carefully. This one here actually represents what? You know, it's actually A intersection B.
Yes.
You know, it's I mean, in this case, it will be A1 intersection B. So you are kind of actually taking the conditional probabilities we had before. Let me just take you back a little bit. You're actually taking the conditional probabilities we have before here, because remember, it is this A intersection B here, when you cross multiply, it gives you that. So this very point here is what we are having multiple of that, okay? Because there are multiple events that are being discussed here. This is known as total probability. So we looked at conditional probability, and then because of mutual exclusivity and collective exhaustiveness, we have defined total probability theory. Okay. Now, with this in mind, we can now define the Bayes theorem. But of course, there's a proof of this. Why the probability of B is equal to all of this. It's equal to the sum of all of this. The proof is that I've already said it. A is mutually exclusive and exhaustive. And if that is the case, if B occurs, it must be happening at the same time with exactly one of the A's. Because B itself is actually the union of, B is a union of B intersection A1 and all the other intersections between B and then A. Whereas the A represents up to the K. Because they are mutually exclusive and collectively exhaustive, that is why that probability makes sense. So in short, the probability of B, which we have, ordinarily we would have defined this as the intersection. I think I showed you this earlier. Do you remember? I showed you this earlier from the conditional probability theorem. The only thing that we are doing now is that we are summing it, which then means that we are summing just this multiplication part. This intersection of B and A, where A can be any of the multiple numbers, okay, is the conditional probability of B given A multiplied by probability of A. But the summation of them is because we are summing this one too. This rule comes from the conditional probability theorem. And that is what helps us to be able to establish the total probability. Do you have a question? Because you're going to do your first test. Derry.
So, please, what's the difference between saying that it is mutually exclusive and exhaustive, and it is only mutually exclusive? Is there?
Oh, I define it clearly. Mutually exclusive means they cannot happen at the same time. So if you take your normal Venn diagram here, if you have A there, you have B there, these are mutually exclusive.
Yes.
Okay. Now, collectively exhaustive means that one of them must occur. So you can even have an intersection, but you can't have a situation when none of them is happening. So either A is happening or B is happening. In other words, there is no empty set, basically. And because so that collectively exhaustive, normally it is implicit. It's not something that is like anything that is not an empty set. Because remember that if you tell me And it's already defined here. Okay. If you tell me that A intersection B is an empty set, okay? If you tell me that A intersection B is an empty set, that's this here. Do you see that?
Yes, please. I can see that.
You are tempted to think that since there's an empty set, then they are not there. But they are there. Or even if they are not there, one is there. That's the point. That's a collective exhaustive. That's a collectively exhaustive. At least one of them is there. It doesn't mean that the empty set means that none of them is there. You should get it.
Yes, please. Yes.
So it is that principle which defines the collective as exhaustive. All right, chapter.
Thank you.
Let's go to the first test. I'm going to give you. So this is it. In a lot of 10 elements, there are 3 defective. I have to now explain it so that you don't get confused as to what I mean by defective. Okay. There are 3 defective. And these 3 defective, you can talk about bulbs. You can use it for a lot of 10 bulbs. There are 3 defective bulbs. Or mobile phones, there are 3 defective mobile phones. They are not proper. Now, this defective here, we are using bad for them. Now, 2 of the elements are selected at random. 2 are selected at random, and we don't replace them. So you select without replacing. So you select and you keep one after another. Now, I can tell you to use some letters to make life simple so that there is no problem. So in order for us not to be too confused, we have a good and then a bad. A bad is a defective one. A good is what do you call it? A good is a non-defective one. So a bad is B, a good is J, just for harmony among all of you. What you're supposed to do now is to find the probability that the first is a good, or the first element that you selected is good and the second is bad. That's the first one. Watch the words carefully. The first is good, the second is bad. So you are finding that. So what is the probability that the first is good? That's the first one. Then what is the probability that the second is bad? Why do you calculate that? The next one is that what is the probability that the second is bad? And the third one is what is the probability that the second is defective or bad, given the first one is good? And finally, what's the probability that the first one is good, given the second one bad? So you're going to work this out. Okay. The information you have, and remember, we have defined something as 3 here. Let me just clarify something very quick for you so that you're not too confused. Please do an independent work without the help of anything. Anything. Do an independent work. And when you're done, you're going to send me the work. I'm going to give you 15 minutes to do that. It's 30, so 45 minutes. That's too much. I'm going to give you 10 minutes. 10 minutes is okay, isn't it? Or I should make it 15.
15, I think.
15 is okay.
15 is okay.
Yes.
Whatever you say, I'll give you 15 minutes. Let's get it rolling. If it was in a class, I'll be going around. So I wanted to look at it as if I'm in a class with you and I'm going around. And if I'm going around with you, it means you're not cheating. Emily, are you working?
Doc,
Emily,
please, you said.
are you working?
Yes, Doc.
Jerry, are you working independently?
So, okay, let me.
Are you
Doc, I'm
working
here.
independently?
Yes.
Albert, are you working independently?
Yes, Doc.
You have 7 minutes. Oh, sorry, it's a 15. Yeah, you have 7 minutes. She has submitted her work. For the rest. All right, time is up. No more working. No more working. So let me just show you the answers I was expecting. And if you got it, you will know that you got it. The first one, you are to find the probability that the first is good and the second is defective. So the probability that the first is good is 7/10. And the probability that the second is defective not the second is defective, because it says and the second is defective. Okay, that is 7/30. So Jerry, which one did you get?
Over 30.
No, I mean, which one did you get? The 7/10.
So I have 7/10 times.
No. I'm just, there are two answers here.
Yes. So I have 7/10. And finally I have 7/30.
Okay. Let me see. Okay. I think you're right. Albert, you got.
I got 7/30.
Yeah, you got a 7/30. But you got a 7/10. You got a 7/10 first before you got a 7/30.
Yeah.
Emily, you got 7/10 first, 7/30. Okay, so you all got that one. So everybody is safe there. The second one is a probability that the second is defective, isn't it? What is the probability that the second is defective? So if you should work that very well, you get 3/10. Emily, you have 3/10. Jerry, what did you get?
Ten.
I can't even see your own. It looks like.
Okay.
Where is your part, Jerry?
Look, I had 3/10. So I think I've captured that side for you again.
You what?
I had 3/10.
I can't see.
I've recaptured that part and sent it to you.
Oh, no. You can't say that you're about to send me that one.
No. I mean, I sent it already, but because you're not seeing, I took a picture of the down one, the calculation down, and sent it to you. I'm done. That's the question 2. I've done question 3, question 4.
And now sending me a different one.
No. That is the continuation of the calculation up there. Because you're not seeing it, I had to take another picture.
But I thought that when you sent it to me earlier, you would have included a continuation.
Yes, I thought I did. Because you're not seeing it, it prompted me to recheck. But I realized that I observed that the 3 continued. The down one was not captured.
Okay. And then that of Albert. Albert, you're number 2. I can't see much of it. Okay, you have to go them there.
Yes, sir.
Okay, so you're gonna number 2 as well. Number 3. What is the probability that the second is defective, given the first is good? The second is defective, given the first is good. That is 1/3. Now, Albert, you didn't break it down. You have 3/9.
Yes, sir.
I mean, there's no problem about simplification, so that's fine there. And that of Jerry, you had 1/3, so that's fine there. And that of Emily, Emily, you had 1/3 this way. Okay, the last one, the probability that the first one is good, given the second is defective. That is supposed to be 7/9. Emily, you had 7/9. Jerry, you had 7/9. Albert, you didn't finish that.
I didn't finish it. Yeah.
Very good. So these are 4 marks of a question. And they all total 8 marks. So Emily, take note of this for me. So Jerry, you had 8/8. Emily, you had 8/8. And then Albert, you had 6/8. All right, let's proceed. If you have a question at this stage, you can ask. Now let's go to Bayesian theory. Yes.
Look, the conditional probability, it looks like sometimes when you use the law of independence, the conditional, my understanding of the conditional is that one will have to occur when another has already occurred. Right. But the independent, the occurrence of one does not affect the other. Sometimes when you use the law of independence, which is probability of, for example, A times B, probability of A times B, you tend to,
as you can see, get the same. You can't use independent because this is conditional, so it's dependent.
Yes. Okay. So what I'm saying, sometimes when you use the law of independence, the answers seem to work. In such situations, are we okay if you use that when you are getting the same answer?
Well, it depends on, it's not about the answer, but if the process is correct.
Okay.
If the process is correct. I don't know whether the process is correct. Is that what you used?
No. I was trying. I was trying some questions and I used it and it worked. No, this one I used the conditional probabilities. I'm just asking if it's the same thing.
No, it's not the same. So you use that. You use the dependency one, the conditional.
Yeah. Okay.
We all know about the Bayesian formula that is a bit of a reverse of the conditional probability. You know that. Okay. If you have 2 events, A and B, you can find the probability of A given B. You can find the probability of A, you can find the probability of B, you can find the probability of A given B. You can find the probability of B given A complement. So if you can find the probability of B given A, then you should be able to find the probability of A given B. The probability of A given B is this. This is the conditional probability as we know. But look at the formula there carefully. The bottom part is unknown. It's not given. Now, what do we mean by it's not given? Because we don't know the details of that, whether it is dealing with, just a second. So because of the fact that this word probability of B itself is not given. If you look at probability of A, it has been given because the probability of A given B, so that one is given. But then if you look at probability of B, it's not given. We are not told probability of B given what? No. So it means that we need to be able to find the probability of B given something. Okay. We know that the probability of B is actually the probability of the intersection of B and A, and that of B intersection A complement. We know this. If you take your Venn diagram, you see that is always so. Okay. So the probability of B itself, B is when you have the intersection of A and B. So if I'm actually talking about B, which is this right-hand side here, this B is this intersection plus the intersection of B and A complement. Now, what is A complement? A complement, in fact, if I were to just showcase A here, what would be the A complement? Let's say this is 1, 2, 3. What is A complement? Emily.
Doc 3.
3.
Good. So if I take A complement and then I take A complement intersection B, what is that?
That will be the whole of B, including the intersection part. Yeah. So 2 and 3.
And that is what we are indicating here, the whole of B. Yeah. Okay, so we know also that this probability of A intersection B, we know from previous conditional probability, even from here, okay, when you cross multiply, is actually the multiplication of BA. Remember, this is actually A intersection B, which is A given B times B. Okay, so it means that intersection of B intersection A will be B given A times A, which is this. You can take this principle of this intersection here and pick it here. Watch it, it's the same thing, it's the same intersection, just that this one is A complement. So if this one is B given A times A, then this one will be what? It will be B given A complement times A complement. Does it make sense? It should make sense. And that is an interesting revelation, because now you can break this down and you can now prove that the Bayesian formula for the two events is made up of this. So the probability of A given B, okay, look at the top here. It is this conditional probability that I'm replacing the numerator here. I'm replacing this numerator here with that, which we know because from this multiplication, we know what that is. We know what that is. And that will be divided by the total probability that we have just spoken about. This is the Bayesian formula. Okay. Now, in other words, anytime you have a conditional probability formula, you can now manipulate that to find a Bayesian. Let's look at the element of the Bayesian formula. The first part, the probability of A, is the prior probability. That's the probability or the belief we have before. The belief before. Okay. That is, just go back for it to see. So the probability of A is a belief before. That we know, the belief before. But then the probability, then you can now, after you had a belief before, you can now have an evidence and then you can update your belief. For example, you can say that I don't believe in God. That way, I don't believe in God is your belief before. Now you are giving some evidence, you now update to the original belief, giving the evidence. So it becomes what? A posterior probability. Okay? So the posterior probability is your updated belief after the new event has been given to you. Given, you see, given that you have evidence. So the probability of A is different from the probability of A given B. The probability of A is a prior probability. The probability of A given the evidence at hand is a posterior probability. And now we can now take it to multiple events. This is just A and B. Okay, so we can say that if we let A1 all the way to K, again, be mutually exclusive and collectively exhaustive events with the following probabilities, and let B be any other event that is also positive. In other words, it's occurring. Then the posterior, that is what we might call a conditional, but the posterior probability of A, given that B has already occurred, is given by this. Now remember that at the bottom here, you have the probability of A given B given A multiplied by the probability of A as multiple times as possible. As multiple times as possible. And then at the top is that same thing, but it's for that particular event at hand. So that one is not from 1 to K. It is a denominator that is from 1 to K. This posterior probability emanating from the Bayesian model, a Bayesian formula, is very useful in certain situations. Let's take an example and you can appreciate it better. Suppose you have a box and this box contains 4 red balls and 6 green balls. Now, let's try to use R for the red. Okay. And then we use green. So what is the total balls here?
10 balls.
10. Keep that in mind. We select 2 balls at random without replacement. One after the other. We are going to draw a tree diagram indicator. Remember that R1 will be the selection of the first ball. R2 will be the selection of the second ball. We've done this before. And then G1 will be the selection of the first ball. G2, the selection of the second ball. If we are to use tree diagram, we'll start with where we had nothing, okay, from 0 point. And then the probability of picking a red ball is going to be 4. I mean, the first ball you are picking, if it is red, is going to be 4 over the 10. What will be the probability of picking a green? What will be the probability of picking a green ball?
6 over 10.
Are you saying it because you saw it or you know it?
Oh, no, I mean,
No,
there are
Doc, we
10
do. 6 over 10.
and 6 green balls.
And that will be represented as what?
J1.
G1,
Yeah, but technically it's not G1. It's actually written as what?
probability of G1.
P of J1.
P of G1. Okay, good. Now, so let's go to the probability of the second ball, given that the first ball was red. So the probability that the second is red, given the first is red. So we are still going to stay on this R1, okay? Given that the first is red, what is the probability that the second is red?
Okay, Doc, that's going to be 3 over 9.
3 over 9. And that is written as what?
So it will be P of R2 slash R1. So P of R2 giving R1.
That P of R2 given R1 is actually written as P of R1. R1. You've done it before. In fact, that was the last thing we ended with, the last time we met. Okay. R1, R1. But I get you, but it's actually not written as what you have said. You said that it is P of R1 giving what?
No, P of R2 giving R1.
P of R2 giving R1.
Yes.
Mm.
That's a probability that the second is red, given that the first is red.
Your answer was what?
Look, 3 over 9.
Yeah. So that's 3 over 9. Okay. And that is sometimes written as R1, R2. R1, R2. Okay. Now watch it. I'm using the word R1, R2 to represent the fact that the R, watch it carefully. You use the word given to make the R2 come first.
Yes.
But I'm using R1 because we did this thing, because when you do the manipulation, it will sense it out. We call it a simple event. We'll sense it out, and then we'll give you that same formula. I'll come back to that because I need to explain that well for you to get it. So you have R1, R2. Now, when you now multiply the two, what do you get? When you now want to calculate the probability of R1, R2 itself, what do you get? Oh, sorry. When you want to calculate, when you want to multiply the two together, when you want to find the two probabilities together, R1,
it's 2 over 15.
No, check it again. Check it again, not 2 over 15. Not 2 over 15. if you want to multiply through everything on the right R side.
Yeah, don't you get 2 over 15?
Oh, 12, huh?
You do get 2 over 15.
That is 12 over 90.
Yes.
Yes.
Yeah, you let's keep it. Let's not cancel it now. Let's keep it as it is.
Oh, okay.
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 So you get 12 over 90.
Yes.
Okay. Now let's go to the G1. Okay. Let's calculate the probability of R1G2. I think I should have asked you. Okay. What would be R1G2?
4 over 10 times 6 over 9.
R1G2.
Over 90.
Just R1G2.
It's 24 over 90. It's going to be 4 over 6, 4 over 10 times 6 over 9, which is 24 over 90.
Good. That is it. Okay. So it's going to be 24 over 90. That is 4 by 10 and 6 by 9. And then let's look at G1, G2. G1, G2.
6 over 10.
Okay.
Times
Doc,
5
J1,
over
G2
9.
is going to be 5 over 9.
Don't cancel anything. No.
It's going to be 30 over 90.
Okay, yeah. G1, G2 is going to be 5 over 9. What about G1, R2?
G1 R2.
G1, R2.
6 over 10 times 4 over 9.
Yeah, 4 over 9.
4 over 9. Very good. So when you now take the 4 over 9, okay, and then you take it from the original probability, you can now multiply and get the ending probabilities for each one of them. You can get the probability of R1, R2. You can get the probability of R2, G2, G1, R2. Then finally, G1, G2. You can have all of these probabilities in a kind of a decision tree form. Okay, now the R1, R2, sorry, the R1, G1, that is a cross probability. The probability of having red, okay, and green ball. These two probabilities, they are actually emanating from the conditional probability. Okay. For example, the last time we met last week, we were able to find each one of these probabilities in the sample space. If we can pick each one of this, we can calculate the J1 R2, for example, as being the probability of J1 multiplying the probability of R2 given J1. This is a conditional probability. You know that. This is a conditional probability, which when you divide both sides, we actually get the actual conditional probability. When you divide both sides by PJ1, okay, and then PJ1, okay, this cancels it. This one is equal to that, which is a conditional probability, isn't it?
Yes, yes.
So that's why I'm saying that the P1, the probability of J1 R2 itself is equal to these elements. These very elements. So that element, that multiplication you were doing, were as a result of picking the probability of J1 and the conditional probability, the one that gave us the ending values. I'll just show you here. The ending values that you are seeing here. Each of those ending values were coming from these multiplications. Okay.
Yes.
Now, so on the basis of that, we can now find this probability of J1 R2 to be the multiplication of J1 and the conditional probability of R2 given J1. Now, we know this element, which is 6 over 10. We also know this one. Okay? So now we can get this answer, which is 4 over 15, which now I'm canceling. At least I'm canceling at this thing. Now, what is J1 R2? That's this. The 24 over the 90. So 24 over 90 is what?
No, it was 2 over 15.
Was it 2 over 15?
Okay.
90 by 15, what is it?
24 over 90 is 4 over 15.
4, yeah, 4 over 15.
over 15. Exactly. So you use 6. 6 goes into 24, 4. And 6 goes into 19, 15. And that is, so those values at the end are the same things that we are calculating backward here. Okay, so you can use a tree diagram basically. Okay. Just as we have found this G1, G2, we can find the rest. We can find R1, R2 to be 12 over 19, R1, G2 to be that. All of them, but I just wanted to know that all of them are being collected from the conditional probability formula. They are all from the conditional probability formula. Now, the sum of the probabilities of all the branches will eventually end up to be 1. So if you go and take each one of these and you add them, you see that the numerators are all going to be 90. And as for the denominators, they are already 90. And so we are able to now get, so when you want to find any of the total probabilities, you can now sum them. So for example, if I want to know the probability of R2, I can take the probability of R1, R2 plus the probability of J1, R, J2. Now, this is an interesting derivation from the total probability because it's like working backwards. Basically, that's what it means. It's like working backwards. So if you take, for example, this probability of R1, R2, which was 12 over 90, and J1, R2, which was that, we can use that to find the probability of R2. Now remember, in the decision tree, we were not, where is it? We were not giving R2 here, if you check. We were rather giving R1, R2. Do you see that? Or we deduce R1, R2. So it's like now, let's move backwards. The tree, let's fold it backwards. And then we can now find, just as we had R1, and then we got R1, R2, now let's find R2. And in finding R2, this time, you use the R1, R2 that you have found, plus the J1, J2 to be able to find the R2. You use those values backwards to find the R2, which was not deducted or which was not deduced from them. Bayesian theorem is a reverse condition. So we can use Bayesian theorem to find R1 given R2. And that is also here. I mean, it's just picking it from here. The R1 given R2. We can find out if from this we can find R1, G1, R1, R2, any one of them, we can find them using that same tree by folding it backwards. So we can find the probability of R1 given R2. And this probability is not shown in the tree, but we can compute them as follows. First of all, we know the probability of R2 is this. We just found out that. Okay? And we know the probability of R1, R2 is 2 over 15. So we can easily find the probability of what? R1, R2, okay, by using the same Bayesian formula, depending on the conditional probability. And that is going to be the R1, R2 divided by the probability of R2. And so you have your 12 over 19, 2 over 15, 2 over 15 divided by 2 over 5. Did I calculate it well? 2 over 15 divided by 2.
Yeah, so it will cross multiply. Yeah, that is correct.
Yeah, it's correct. It's correct. I don't know why I brought the times there. That's correct. So that is how you find this. Let's look at the last thing on independence. Two events are independent if the probability of A given B equals the following. We already know this. This one we use it multiple times. Now watch it. That or is the same as the probability of A multiplied by the probability of B. We have excluded the intersection. I'm sure you know that. Now, the independence uses multiplication. But if two events are dependent, then the probability of B given A is not equal to, and therefore this is not equal to the probability of A giving B. Let's take an example and then you'll understand. Let's assume that you have the probability of A giving, you have the probability of A to be 40%, probability of B to be 50%. If A and B are independent, what would be the probability of A? If they are independent, not if they are dependent. If they are independent.
Doc, if they are independent, it will be 1/5 or 0.2.
Exactly. It's principally easy. It's 1/5 or 0.2. Now, the reason is because they are independent. They don't depend on each other. Okay. Now, let's look at this. If probability of A is 60%, probability of B is 50%, and the probability of A union B is 8%, the question is, are they independent? Are they independent? Well, the only way you can, because you have been given the union, you have to use the union principle. Okay? You have to use the union principle. So if you're going to use the union principle, then you have to find the probability of AB, isn't it?
Yes.
What is the probability of AB?
Okay, so AB, if they are independent, will be 0.3.
No. Let's write the formula. Probability of AB will be what?
Probability of A times probability of B.
B.
It's not times. Probability of AB. We don't know whether they are dependent or independent. I have not said anything.
Okay.
Okay. Doc, the condition. Okay. Is that independent? Okay.
If you are using a complementary rule, it's going to be the probability of A plus the probability of B.
B minus the probability of A intersection B.
You said A U intersection B.
A union B.
It's A union B.
A union B, rather.
So it's a probability of A union B. That's it. It didn't tell you to find anything. But based on this, that is one thing I can find. And one thing I can find is it. Because the elements have been given. And so once the elements have been given, you can create the formula to match the element. What is the probability of A in this question? It's 0.6. What's the probability of B in this? 0.5. What is the probability of A union B? So when you take the simplification, what do you get?
0.3.
Point out.
3.
Exactly. Now the question is that the question was, are A and B independent? Now that you have the 0.3, you ask yourself, what is independence? Independence is when two events are usually said to be independent if their intersection equals their the multiplication of their probabilities. I mean, you remember we just said, okay, so probability of AB, okay, if they are independent, then this is equal to the probability of A multiplying the probability of B. Is that not so?
Yes.
I mean, up there, I don't want to go up there because I need to clean this one something. We just said this some few minutes ago. That's independence. So, question is, for you to confirm whether this thing is independent, take this from these two guys. When you multiply them, what do you get? Will it be equal to what we've calculated up there? Come on. When you multiply them, the probability of A is what? 0.6. The probability of B is what?
It's 0.3, so it's yes.
Is that not also 0.3?
Yes.
Just as the previous one is 0.3. And therefore, we can say that A and B are what? Are independent. What you are doing is that you are extracting the usual formula, okay, that commutative property formula, and now using the independence formula here to check whether, because you have been given information, so you got to use the information to come out with having the same result. They are all probability of AB, they are all probability of AB. And they all give you 0.3. They all give you 0.3. Therefore, the two events are independent. Okay, you can check it.
Oh.
Yeah.
No. So
Yeah.
the AB, the first AB is also, can we also, is it also the same as A intersection B? I mean, the first AB.
Yes, depending on which property you are dealing with.
Okay.
Yeah, depending on which property you are dealing with. The question is, what property are you dealing with?
You are dealing with, so we are checking whether it's independent. So if
Yes.
you are dealing with independent, okay.
Yeah, you are checking whether it is independent, giving the information. Remember, it's not just go and check abstractly whether they are independent, but giving the information.
Okay.
Giving the information. There's no doubt the probability of AB is A intersection B. Yes, we know that.
Yeah.
But if A and B are independent, then the probability of AB is probability of A times probability of B. Okay. That's how I say it depends on the situation. But note that we can write probability of AB as probability of A intersection B. That's the joint probability, isn't it?
Okay, yes. Yes.
Yeah. That's the joint probability of the event A and an event B. That's all we know. So if A and B are independent, that is equal to the probability of A times the probability of B. In other words, that same thing you are calling probability of A intersection B is the same as probability of A times probability of B, provided that they are what? Independent. But if they are not independent, what happens? If they are independent, this one. If they are independent, then you have probability of AB being equal to the probability of A times the probability of B, if they are independent. But if not, then this same thing is equal to the probability of A, times the probability of B given A. You know that. Got to memorize some of these formulas.
Okay.
So that's what. So once the question gave us this and gave you that, then it means that he's trying to tell you that go and use this formula. Because watch it, in each one of them, I'm using multiplication. But the nature of the question they have given me requires me to use what? Additive property. But so I just need to check the additive property to see whether the additive property matches the multiplicative property here of independence. I checked the additive property, it gave me a value of 30%. You check the multiplicative property, it gave you the value of 30%. They're independent. But you have to understand that the independence being mentioned here is independence differently from whether you are dealing with the multiplication or whether you are dealing with the additive property. Let's move on. We don't have time. I've lowered. I've spent a lot of time on this conditional probability, and I can see that I'm a little bit delaying with the binomial, which we should have started this week. Okay, so let's take another example of Bayesian theorem, just where you still apply the Bayesian. The survey shows 57% of Americans. Don't worry, this is not a test. If it is a test, you will know. I know. Albert was just going to beat me that another test. The survey shows that 57% of Americans have a workplace retirement plan. 68% of all health insurance. 68% have health insurance, and 49% have both benefits. We are going to select a worker at random. Now, if you were to use a Venn diagram, how would you normally have indicated? If you were to use a Venn diagram, how would you have actually written that your Venn diagram? So the Venn diagram will be in such a way that, I'm not drawing it. You were doing retirement plan. That is R. Okay. Let's do an intersection. Okay. Health insurance, that's H. Where would the 49% be?
Intersection.
the intersection. How would you write that?
R intersection H.
And you can say that P of RH is 0.49. Okay, what else will you do? What will be your probability of R? This probability of R is going to be 56, right? 0.56. Now, this probability of R, is it for all of the circle or what of the circle?
For all of the circle.
It is for all of the circle. So that's the probability of R like this. Now, this is going to be the probability of H. Probability of H is 68%. I'm just using Venn diagram to guide you. But then the elements of the writing, you can rewrite it properly. But I'm just using Venn diagram to tell you. So that word probability of R is all of them with a retirement plan. But that is not the same as exactly those with a retirement plan. You know that. This is those who have retirement plan. That is not the same as those who have exactly retirement plan, because those who have retirement plan also have health insurance. So if you want to do those who have exactly retirement plan, you have to take away those who have intersection. I know you guys get what I mean.
Yes.
All right. So this is how you would have represented it. Okay. The probability of R is 0.56, H is 0.68, then the intersection is 0.4. Now there's a rule called the De Morgan's rule. And to be able to address the question, the first question says, what is the probability that a person neither has health insurance nor a retirement plan? Now, if you were to work this in a normal Venn diagram, you remember how we used to calculate it? Do you know that we can find the X value, but this time the X value has been given. So we are finding outside of the X. So if you have the universal set to be this, okay, and here is 0.49, and then here is 0.56, and here is 0.6 per second. It's 0.68. Can somebody do it? I don't even try that. Okay. And then here is 0.49. Then here is going to be 0.56 minus 0.49, isn't it? Isn't it? Remember? Yes, so what value would that be? 0.56 minus 0.49. Take your calculator. Okay. Yes?
That would be 0.07.
So you have 0.07. And then here will be 0.68 minus 0.49. What would that be?
9. 0.19.
0.19. So we don't know what is in the none, neither. Okay. We don't know this value. We are not told what the universal set is. But ideally, if we are to find the universal set, what it means is that 0.07 plus 0.49 plus 0.19 should be equal to, plus the X should be equal to the universal set.
Doc, since we are dealing with probability, is it not the assumption that the universal set is 1?
Exactly. I was going to ask the question.
Okay.
So if the universal set is 1, then you should be able to find the value of X.
Yes.
So do that. Okay. Add the 0.49 to the 0.19 plus 0.07 plus X equals to 1, and find X. I just hope that, I mean, the other ways of doing it, I'll come and show you the other ways, but I just want to show you. What did you get?
I got 0.25.
Yeah, that's exactly the point. And in fact, I'm about to show you that using the probability principles of the De Morgan's rule, it gives us the same thing. So we come here, we've already identified this, okay? So using the De Morgan's rule, according to Augustus De Morgan, okay, we can say that the probability of R complement, that is a retirement complement intersection health complement, is a union of the R and H complement, which is a 1 minus the probability of the unions. In short, what are we looking for? The question says those who are neither, okay, the X that we found. So neither means that they are not what? They are not part of the intersection. So the probability of an intersection, the probability of R complement. R complement is anything that is not in R. H complement is anything that is not in H, but it's in the universal set. The intersection of that. And this will give you the union, 1 minus the union of that. You know, the union is more or less the combination of R and H, but anything outside of that, but is in the universal set. Do you know what I mean? That's why we indicated that the universal set is equal to 1. So this one, when you just substitute it, we can now say that we can find this value. This value here, watch it. Probability of R union H is this. Is this. We know this is the probability of R plus the probability of H minus the intersection. We know this. It was given to us. That gives us 0.75. We know that. And therefore, if we want to find those that are not there, we get 0.25. This is a little bit complex. I hope you understand. But that is why I used the Venn diagram for you. The Venn diagram was easy because you all remember two-set Venn diagram.
Yes.
Albert, do you understand the Venn diagram one?
Yes, Doc.
That one was easy.
Yes, Doc.
Life is not always easy.
Yeah.
And that's the same thing you got here. That is a De Morgan's rule. It helps you to find what is not in any of the sets. But it's the same thing. They all lead to 25%. 25%. Okay. So that was the question you were being asked. The next question is, what is the probability that this person has health insurance if he has retirement plan? So that's conditional, okay? If he has health insurance, if he has, I mean, you can again go and try the Venn diagram. But that is a conditional probability, so it's here, it's simple. If he has health insurance, if he has retirement plan. So R is what he has already. That is a given. Given that he has R, what is H? And that means that you have to use the intersection, and we already know the intersection. Okay? Because from here, we have calculated, we're given the intersections here. And then we just divide that by the H, the R. That is 0.56. And that will give you this value. The next question. The next question simply says that having health insurance and retirement plan independent. Again, we come to that same conclusion with that. Are they mutually exclusive? I mean, that's obvious. But let's look at, are they independent? Okay. Because this has given us this value already, it's 7/8, okay, which is the independence, I mean the conditional probability. And this value is not the same as the probability of H. Remember the probability of H? That was given to us as 68%. Okay. Now, the probability of H given R is not the same as the probability of H. Okay. And because that is the case, the events H and R are not said to be independent. If you don't understand that, they are not said to be independent. They are not independent. In other words, they are dependent. Look at the H and look at R. Okay. And then the last one is, are they mutually exclusive? This one, it should be obvious for one of you to tell me. The two events, are they mutually exclusive?
No, please, no.
Okay. Why? You're right.
Because they have an intersection.
Exactly. That's the point. Since we have an intersection, which is what she said, and the intersection is not 0, okay, then the events are not mutually. Conditional probability, Bayesian theory, independence, very, very important. Okay, so try this question on your own. This is your assignment for today that you want to try. You're not done yet, but I just want to put this assignment before we proceed. No, that's not even an assignment for you to do. That's not, okay. So this one, work it. You work it. So let's look at it. An oil exploration company currently has 2 active projects, one in Asia, the other in Europe. Let A be the event that the Asian project is successful, and let B be the event that the European project is also successful. Suppose A and B are independent events with probability of A being 40% and B being 70%. Now, if the Asian project is not successful, what is the probability that the European project is also not successful? You should be able to reason and explain your answer. Of course, we are going to do it together. Okay. Now, how would you go around it? First of all, the 2 events, are they dependent or independent? From the information, are they dependent?
They are independent events.
They are independent. What makes you say that?
Because it says that suppose that A and B are independent events.
Good. It's there. It's clearly there. Now, the A complement, okay, you see the probability of A, that's the Asia. The probability of B, that is the Europe. Okay. Now, suppose the A complement and the B complement, what would they be? Would they be dependent or independent? It should be obvious.
Still independent.
It will still be independent. Okay. It will still be independent. So let's go back to the, it says that if the Asian project is not successful, that is a complement, isn't it?
Yes.
What is the probability that the European project is also not complement? And explain your reason. But the reason is what we just said. Because A and B are independent, then their complements are also independent. You can prove that. So if you take the probability of B complement giving A complement, that is actually going to give you the probability of B complement. And that is an indication of independence. And therefore, 1 minus the probability of B complement is going to be 30%, which gives you back what you had. Okay, so both of them are. So question of, what is the probability that the European project is not successful? It's just calculating the probability of B complement. And the probability of B complement is this. It's 1 minus 0.7. Okay, next question. It says that what is the probability that at least one of the 2 projects will be successful? At least one of the 2 projects will be successful. What is the probability? Jerry, are you here? Hey, I've missed the guy.
Doc, I'm here. I'm here, pa.
I'm
following.
What is the probability that at least one? The word at least here is talking about what? The fact that we are dealing with at least means we can go to infinity. So
one or more, yeah.
Yeah, so it's talking about what? What's symbol?
Their union.
Exactly.
Their union.
At least one of the 2 projects will be successful. So he's talking about the union of what? The union of what?
A and B.
Exactly. So we are looking at the probability of A union B. So basically, this question is asking, what is the probability of A union B? Remember, the 2 events are independent. First of all, the probability of A union B is calculated as probability of A plus probability of B minus the probability of what? A intersection B. Which happens to be the probability of A, probability of B. Do you remember?
Yes.
So what is the probability of A here?
0.4.
0.4.
Huh?
It was given as 0.4.
0.4. Okay, good.
Yeah.
What's the probability of B?
0.7.
0.7.
0.7. And what is the probability of A, probability of B, or probability of A intersection B?
That's probability of.
Because that's what we are minusing. Minus the probability
Okay.
of A, probability of B. What is the probability of A? 0.4 now.
0.4.
Yeah.
And what is the probability of B?
0.7.
So the two of them, what do we do with them?
That we multiply.
We multiply, and we take that out from the rest. You know, so.
So now.
What does that now mean?
Okay,
Right,
I want to register my presence that I'm here.
I know. It's good. So that will give you this. You have the probability of A plus the probability of B minus the intersection. That will give you 82%. Okay, it's understanding. Last one. Given that at least one of the two projects is successful, what is the probability that only the Asian project is successful? What are the chances that only the Asian project is successful? Now, this is quite a tricky one. Very tricky one. Because this is tricky. Who has an idea? First of all, he's saying that at least one of the two projects is successful.
So, Doc, the given part is going to be A union B.
Yeah, the given part is going to be A union B. You're right. Now, what is the one before that? You're looking at the probability of A, B complement.
Yes.
Okay. Because
that's only the A part without the intersection of B.
Correct. So that is A, B complement. Okay. For those of you who are following, we're looking at probability of A, B complement, giving the probability of A union B.
A union B.
Once you get this, the rest is about how you split them, which is good. Well, remember that this alone itself is what kind of probability here? As it stands, what kind of probability is that?
Conditional probability.
So conditional probability.
And use the principle of conditional, you can split it. So the numerator is going to be what? Remember,
P of A union B.
No. Take your time. Remember that the conditional probability, the numerator is usually A intersection B.
Okay.
Divided by the probability of B. Do you remember?
Yeah.
Yes.
But this one, the elements are many. So the numerator can be A intersection B.
So it's going to be probability of A, B complement intersection, probability of AU.
AUB. Yeah, but you don't add probability because you've already mentioned the probability.
Oh, okay.
So say that again.
So it's going to be AB complement intersection AUB.
So it's going to be probability of
B
complement
intersection
A
union B.
Exactly. That's going to be the numerator. And then the denominator.
P of A union B.
Exactly. P of the same thing. That's it. The same thing. And at this stage, you just look for the element. So first of all, what is that probability of the numerator? To be honest, when you look at the numerator very carefully, that A union B, the intersection of A union B, they can go. They can go. They can go. So the numerator can be the probability of A, B complement. Check it. Because look at it. Everything you are talking about as A union B, the intersection, the intersection of whatever it is in A union B, it is the AB complement. Guys.
Okay. Yes.
You don't need the intersection because we already captured it.
Yes.
This part here, let me just use a different color. This part here, you don't need it because B complement itself is anything that is not inside B, but it's in the universal set. Isn't it?
Yeah.
So why do I need this one now? Because B complement itself is capturing anything in the universal set that is not inside B. So it's not just what is inside A, it is what is not inside A, but it's even in the universal set. So why are you talking about A union B now for me? This intersection with A union B. I don't need this A union B. Are you following? I should go over.
Please go over.
Okay. Now let's take a Venn diagram. Okay. This is a Venn diagram. This is A. Do you see what I'm writing, by the way?
Yes.
Yes.
Okay. You have A, you have B. Now, if you take B complement, okay, let me just take 1 and 2 here. Okay, and then do 3. B complement, and then actually there's something here in the universal set I've not mentioned, because the universal set, if it is not in A or B, it doesn't mean that it's not in the universal set. So what will be B complement? What will be the element of B complement?
Doc 3.
Not 3 alone.
Okay.
3, 1.
Yeah, 3 and 4.
No, 3 and 4, exactly, 3 and 4. So already 4 has even been captured though. 4 has been captured. So let's put that down. So that's 3 and 4. Now, what is A union B?
A union B is 3, 1, 2.
Okay, so now watch. It's 3, 1, 2. Now, so that A union B, that is this one here. That's the A union B. It's only 3, 1, and 2. Now, B complement is 3 and 4. What is A?
A is 3 and 1.
Good. So it's 3 and 1. So when you are asked, when you are asked A complement, not A complement, A B complement, like we just written up there. Okay, what will be the element of A B complement?
Doc 4.
4.
What are they?
It's 4.
It's 4.
Where did you get a 4? I'm asking.
Okay. A
So,
P complement.
AU complement means that elements in the universal set which are not in A union B, and
I'm talking about A B complement. Okay, this one here.
AB. Okay.
Doc,
Sorry.
that would be 3 and 4.
That will be
3 and 4.
3 and 4.
what about 1?
Doc, please come again.
What about 1?
Okay, so Doc, we are looking at B complement. So since 1 is included in B, it won't be part.
But then it is included in A.
Yes.
It's also included in B.
It's also included in B. So my question is, what are the elements of A? It's 1 and 3.
Yes.
What are the elements of B complement?
B complement.
B complement is 3
3
and 4.
4.
So what are the elements of all of them?
Okay, so it will be 3, 1, and 4.
3, 1, and 4.
Yeah.
Mm.
And you can see that the 4 hasn't been captured by the A union B.
Yes.
So that's the point I'm saying. Okay. So let's go back here. Let me just wipe it all. So when you come here, we are looking for, first of all, let's go back here. At least one of the 2 projects is successful. So first thing, okay, let me just show you. So you have A complement, the probability of A B complement given A union B, we've already established that this is it. If we are doing the intersection with AUB, there are more information in AB complement than you can get in AUB. There are more information in here than you can get in here. So on the basis of that, we can then say, oh, no, wait. Let me just clarify something. Yeah, actually they are, okay? If you are to take AB complement intersection A, union AB complement intersection B, you know that can be formed here. What I just said, AB complement intersection A, AB complement intersection B. And I'm on. Don't worry.
Yeah.
But then whatever thing is here is already in there, and therefore the whole thing now boils down to this numerator, which is the AB complement. AB complement. What is AB complement? Now, as for A union B, we already know it from here to be 82%. But what is AB complement? Given the information that we originally had, let me just take it back to the original information. Probability of A is what? 0.4. Probability of B is 70%. What will be B complement?
30%.
1 minus 0.7, which is
Which is what? Which is what he said.
0.3.
Good. So what is probability of A multiplied by that? Is it not 0.12?
Yeah.
That is 0.4 times 0.3.
Times 0.3. Yeah.
That's 0.12, right?
That's dope.
That's still that's still 0.12, which is this.
Yes, Doc, it's 0.12.
Yeah. So the numerator here becomes 0.12 divided by the A union B, and that gives you 32%, giving you finally 0.146. All right. So that is how you are able to design and understand these independent elements. I have this for you. Is it an exercise to do? Let me see. Oh, yeah. So this is your only homework. I think I've written homework there. Yes. This is the only homework that I want you to do. It's similar to what we've just done. Execute this from your head and submit that in our next meeting. Now, I also have this for you. I'm not going to teach parallel systems. So I want you to learn parallel. Okay, sorry. It's parallel systems on your own. I have the notes here. I have the notes here, so check it, look at it, check it, and look at it. Okay. I have some examples here for you to look at. Check it, look at it, check it. I have some solutions here, check it, check them. And then it's just a very simple thing, process. And then you can try your hands on these things. Don't submit them. Try your hands on these things in the test. Next time we meet, we are going to start with binomial. We're going to start with random variables. All of these are classical probabilities. We're going to start with
No, please. Which test is that? Like which